All right, so hopefully at this point you are done. I'm going to unfreeze my screen. Um, okay, so at this point, I'm going to add things to this diagram. Please don't add anything to yours until I say so. I will make sure you have enough time to kind of add the stuff afterwards, okay? So keep in mind, we're talking about the kidney. This is the whole diagram of the nephron. Okay, we're going to be talking about how the blood is filtered out by the nephron, as well as what are the things that goes in and out, and by what process. Okay, so first part here. This is the blood vessels that feeds blood to the nephron and take blood out. The wider part here, this is called the afferent. I'm going to zoom in a little bit more. This is the afferent arteriole, ARTERIOLE. Make sure you just hold off for a second. This is the afferent arteriole, so blood goes in this way here. And the narrower part here, this is the efferent arteriole. Okay. A couple of ways for you to remember that. You can do A before E. Okay, A before E, so afferent, efferent. Or you can think of E as exit, so that's where blood exits. And this part here, this blob with some kind of holes in it, that is the glomerulus. Oops. Glomerulus. Okay. Remember, glomerulus is basically a ball of blood vessel. It's a ball of small capillaries. Okay. So, yes. Glomerulus. Just hold off until I gave you time to copy things down, okay? So, now on the wall of these glomerulus, there are little slits. There are little slits called fenestrations. Now, how many of you have ever visited a castle before? Yay, okay, one or two of you. Or seen a picture of a castle? You know, on a picture of a castle wall, there's usually slits where people can shoot arrows out or something against attackers. Those little slits, in English, is also called fenestrations. Okay, so whoever named this definitely have that castle wall slits thing in mind. So these little slits here on the glomerulus is so that when afferent arteriole bring the blood in, the blood pressure will push the fluid out of the slits of the fenestration and into this part here, which is called the Bowman's capsule. And this is also the reason why at the afferent arteriole, the blood vessel is wider, and the efferent arteriole, the blood vessel is narrower, because wider, narrower, which means there's a lot more blood pressure on this part here. So it will be pushing those fluids out of the fenestration, okay, into this section, which is called Bowman's capsule. Okay. So the process that happens where the fluid get pushed out of the fenestration of the glomerulus into the Bowman's capsule, this process is called ultrafiltration. Think of in chemistry when you're filtering out something. Okay? It is really a filtration process, but under high pressure. Okay? So by the time it gets the fluids that get pushed out of the glomerulus into the Bowman's capsule, You call that the filtrate. And at this point, what's in the fluid? In the fluid, at this point, you will have water, you'll have urea, you will have sodium, potassium, Cl minus, fluoride ions, you will have glucose and amino acids. Okay? AA amino acids. Now, bigger things like red blood cells or big protein molecules will not fit through the fenestration, so those things are going to be kept here. But anything smaller than the size of the fenestration, like these chemicals here, they will get filtered out and get into the Bowman's capsule. Any questions so far? Now, and since this is a filtration process, I'm going to use blue because it's a passive transport. Blue is passive transport. So ultrafiltration, that's blue. Okay. Any questions so far? So please copy that down. Please copy that down. I'm going to also try to find the word fenestration. I just want to make sure that I spell it correctly. Would I be able to spell all that in here? No, I'm just going to write it here. I don't have enough room here, so fenestration. FENESTRATIONS on glomerulus. Okay? Okay, so let me know. I'm going to zoom in a little bit more. Hopefully that will give you clear vision in terms of what's going on. Something you can't read?
Yeah, the
GLOMERULUS. Let's see if I can write it better. GLOMERULUS. Okay, I was able to. So that's. Yeah, remember the prof that I was saying before, who can draw amazing drawing? He was able to like make sure he leave enough space for everything, and the line doesn't cross. Okay. Other words that you guys can read. By the way, who's done? If you're done, can you put up your hand, please? Okay, so most of you. Okay, if you're done, just leave your writing and drawing utensil. Okay. Now, the next part here, the filtrate, after it gets in the Bowman's capsule, it's going to go through the first set of tubes here. This is called, again, just wait for a moment. This section is called the proximal convoluted tubules convoluted tubules. Proximal, remember, it's closer. Convoluted just means complex. Now, at this point here, if you look, you have in your filtrate, you have glucose and amino acids. Those are nutrients. You don't really want to lose your nutrients when you're trying to the whole main point is to get rid of the nitrous waste, which is your urea, and make sure you don't lose too much water. So you really don't want to lose that glucose and amino acids. So what happens is that at this point here, your glucose and amino acids is going to leave. Okay. Also, some water will be reabsorbed, and also some salts going to get reabsorbed. Okay. So by the time it's done, the convoluted tubules, what are you going to have in your filtrate? You're going to have still going to have urea. Okay. Now you're going to get less water. You're losing some water, or less water and less. Now I just wrote salt. We're going to focus on sodium ion, potassium ion, and chloride ion. Okay. So in this case, now glucose and amino acids, those will be actively transported. They are going to be pumped out of the filtrates. Okay? The sodium and potassium, those are going to be also active transport, pumped out. Okay? Water, it will be a passive transport movement. Okay? Osmosis, so to speak. So that's what happened at the proximal convoluted tubules. So please add this information at this point. If you have questions or you can't read part of the thing, let me know. So Bowman's capsule, proximal convoluted tubules. Okay. Put up your hand if you're done. It looks like a lot of you just looking at me. Okay, so maybe 15 seconds more for those of you who. All right. So after that, your filtrate gone through proximal convoluted tubules, still have urea, less water than before, less salt than before. So at this point here, your filtrate is still fairly diluted. It's still comparatively dilute. It's more watery than salty. Now, one thing that I haven't included, like why on earth is there a line about top quarter of the page? This line here separates, I'm going to go onto the side here because we don't need as much room writing as on this side. This line here separates the cortex of your kidney. Remember, the kidney on the outside part is the cortex, and on the inside part here, that's the medulla. Okay, so you have the cortex above, medulla below. And we're going to talk about the cortex and medulla and how this comes into play in this section. Okay, cortex and medulla. Now, cortex and medulla. So in this part here, the filtrate is still pretty diluted. Now we're going to talk about this section here, which is called the descending loop of Henle. Descending loop of Henle. Now hold off before you write or draw anything. The descending loop of Henle is rather interesting. In fact, both parts is interesting because the descending part of Henle, the membrane only lets water going through, but not salt. Okay, water can only going through the descending loop of Henle, but not salt. So this have interesting implications. Loop of Henle. Henle. So it's permeable to water, but not salt. Okay? So what it means is this. Throughout the descending loop of Henle, water will be leaving the filtrate as it goes down. Okay? Now, water is leaving the filtrate at this point through osmosis, which is a passive transport. So I have blue underlined in blue. So by the time it gets to the bottom of the loop of Henle, by the time it gets there, your solution, your filtrate is very concentrated. It's very salty, so to speak. Think of it as very salty. And at that point, what is in this liquid or fluid? You will have urea. Urea is pretty much staying there the entire time. You have sodium, potassium, and chloride ions, basically your salts, but much less water. Remember, all those water left the descending loop of Henle by passive transport because of the membrane. Okay, so at this point, I'm going to ask you to copy that down. Okay, so cortex is up there, medulla is down there. Also, again, let me know if you can't read some of my words or handwriting. Yes. Very concentrated. Yeah. So remember, up here it's quite diluted. Down here is very concentrated, very salty. Who's done? Put up your hand if you're done. Okay. 10 more seconds, 15 more seconds. So, descending loop of Henle, permeable to water but not salt. Now, the ascending loop of Henle, this is also quite interesting. And also make sure you wait for a bit, okay? Wait for a bit. I'm going to try and make sure that the medulla and cortex is here. Now, the ascending loop of Henle is the opposite. Ascending loop of Henle, salt can go through, but water cannot go through. Okay? Salt can go through, water cannot go through. But this is a weird part. I'm going to tell you. Let me write it down first. Ascending loop of Henle. So again, permeable to salt, not water. Okay? So what it means is this. Salt will, of course, in this case, leaving the filtrate at this point, but make sure you don't copy things yet, okay? Because there is a weird and tricky part. Now, look up here for a moment. So when you're down here on the bottom part of the loop of Henle, the filtrate is very salty, right? All the water has been going. So in this case, because it's so salty inside compared to the outside, the salt will be leaving by passive transport. Okay? On the bottom of the loop, ascending loop of Henle, the salt will be leaving by passive transport because it's so concentrated inside here compared to outside. This is important simply because it keeps, oh, by the way, I should write this here too, sodium, potassium, and chloride ions. So why is it important? It keeps the medulla very salty. Okay? It keeps the medulla very salty and maintaining that concentration gradient. After all, water has to get out of here by passive transport. So the tissue must have quite a bit of salt. So by the fact that the salt is leaving here, it keeps the medulla very salty. Also, by keeping that concentration gradient, help water to move out of descending loop of Henle, okay? Because of that concentration gradient. Okay? You have to have that concentration gradient, otherwise water won't move. Yes? Ooh, that's a good question. If you think about the whole kidney is to make sure you get rid of waste, but also the osmolar regulation. So that also depends on how much fluid intake you have been having, and also, of course, like how much salt have you been consuming, that type of thing, right? So it really depends on that to play that balancing act. In terms of what we're doing right now when we're talking about ascending loop of Henle, it's just this: you must pump out, or you must have enough salt to leave so that you can have that concentration gradient. Okay. Also, by the way, on the bottom part, salt is leaving by passive transport. But as it goes up and up, at this point, the filtrate is not going to be as concentrated or salty as before. So by the top part of this ascending loop of Henle, still in the medulla, the salt at this point have to be pumped out by active transport. Okay? Because up till a certain level, it won't be salty enough for the salt to come out by passive transport. You have to pump it out. You guys follow that? So by the end of the ascending loop of Henle, let's just say here, your filtrate, you still have a lot of urea, filtrate, urine, or you have less salt. Okay? Sodium, potassium, chloride ion. There are other salts too, but we're not really considering that. Also have some water. Okay? So, let's see if we can. Okay, so please copy that down. Let me know if you can't see certain things. Yes.
What's the word after keep?
After what?
Keep.
Keep medulla very salty, maintaining that concentration gradient. And because of that concentration gradient, then water would be able to come out of the descending loop of Henle. How many of you are done? Okay. Now, after the ascending loop of Henle, where this little funny section here. So this here, proximal convoluted tubule, the further away one, that will be called the distal. distal convoluted tubules. Distal convoluted tubules. And at this point here, this is the weird part because sodium and potassium will be pumped in. Okay? Sodium and potassium will be pumped in, but at the same time, sodium will get also pumped out. Now, how much does it pump in? How much does it pump out? That again really depends. Okay? The idea is to maintaining that balance that you have the right amount of sodium and potassium in your system. So if you happen to have more sodium in your system at the time than you should have, then they will pump more in and less out. If you don't quite have enough sodium in your system at that time, they will pump out more than pumps in. Okay, it's really to play that fine-tuning balance. At the same time, water would also be leaving. Okay, water would also be leaving. Okay, so sodium and potassium, they're all pumped in and out. The water is always through osmosis, so that's okay. It's always passive. So that by the time it passes through the distal convoluted tubules, what on earth do you have? You still have urea. Urea, you really want to get rid of that stuff, so you still have some sodium and potassium. It really depends on what's going on your system at that point, and less water. Okay. So you can add that information onto your diagram now. Okay. How are you guys doing? Good. Who's done? Okay. Last but not least, and this one is relatively simple. We are at the last part here, the collecting duct, and this we officially can call whatever it is, urine. So collecting duct. Collecting duct. Okay. Now, collecting duct, it is to collect urine from a number of nephrons. So you can see here, you have nephron coming in to this collecting duct, but you also have nephron coming in from this other nephron. Okay, collect urine coming from here. So there's a number of nephrons connected to the same collecting duct. And during the collecting duct, it's really the last little bit of reabsorption, mostly water. Okay, mostly water. and the water is absorbed by osmosis. So it's passive. You also have a last little bit of salt reabsorption. And those are active transport. It gets pumped out. Oops. Now, this part here, the water getting reabsorbed, I'm going to put a star here because keep in mind how much water get reabsorbed or how much water is allowed to be peed out is influenced or regulated by a hormone. This hormone is called ADH, antidiuretic hormone. Antidiuretic hormone. So let me just write down the name here since I do have the space for it. Antidiuretic hormone. Okay, antidiuretic hormone. So when antidiuretic hormone is there, by the way, diuretic means to go pee. So antidiuretic hormones means you're trying not to pee. You're not trying to pee. You're trying to not to lose water. Okay, so when it's there, you don't pee out as much liquid. But when the antidiuretic hormone is not there, you would get rid of the excess water more. Okay, so this is the part of the osmotic regulation part comes in. Like you don't want to have too much water. Okay, so antidiuretic hormone, which is produced by the pituitary gland, will regulate that. Also, this is a part, if you remember from the video, if you have consumed ethanol, ethanol will interrupt the antidiuretic hormones. In this case, you will just keep losing water, which in some ways, it's one way your body getting rid of that ethanol. Okay? So, by the end of this whole thing, extend this a little bit. What do you have here? So, at this point, you will have, you still have urea. Urea doesn't really seem to go, which is good. Less water, as it should, and sodium and salt. Okay? So whatever it comes out should be mostly urea, sodium salts, and various salt, and some water. Again, depending on how much water you have in your system. If you have a lot of water in your system, you'll have more water coming out. If you have not enough water in your system, then you have less pee coming out, less water coming out. How are we doing? Yes. After the which part? The okay. I'm going to, because I'm recording this, so I'm going to go through the whole thing once. So in the beginning, you have the afferent arterial bring blood in, efferent arterial bringing blood out, glomerulus. It's wider here and narrow here, so create that blood pressure for the filtrate to come out of the fenestration on the glomerulus into the Bowman capsule. The process is called ultrafiltration. It is a passive transport process. After that, the filtrate goes through the proximal convoluted tubule That is mainly to reabsorb the nutrients and some water. So the nutrients, glucose and amino acids will get pumped out of the filtrate. Your water, some of the water would also be passively transported out. So by the time before it gets into the descending loop of Henle, you have urea, less water, less salt in there. You shouldn't have glucose or amino acids. Then it goes down the descending loop of Henle. The descending loop of Henle allows water to leave, but not salt. So water will be leaving the filtrate throughout the descending loop of Henle by passive transport. So by the time it comes to the bottom of the descending loop of Henle, your filtrate is very salty or very concentrated at this point. That is important simply because by the time it goes up the ascending loop of Henle allows salt to leave, but not water. So on the bottom part of the ascending loop of Henle, while the filtrate is very salty, the salt will come out by passive transport. And the top part of the ascending loop of Henle, by then, the filtrate is not that salty anymore. It will have to be actively pumped out. Salt will have to be actively pumped out. This process of salt leaving is to keep the medulla very salty and maintaining that concentration gradient. And that concentration gradient in the medulla is important because water needs that concentration gradient to come out of the descending loop of Henle. Okay. So by the time it goes into the distal convoluted tubule, your filtrate, urea, less salt, some water. Distal convoluted tubule, you'll be doing the fine tuning of salt concentration. So some salts, sodium and potassium, are pumped in, but some sodium is also pumped out. Really, depends on the system you have in that time. And water is also leaving during passively. Okay. Last step, going through the collecting duct. The collecting duct is mainly to do the last little bit of water reabsorption. This water reabsorption is controlled by antidiuretic hormone, which is produced by your pituitary gland. Also, some salt, sodium, potassium, and chloride ion are also actively pumped out. So by the time your urine comes out, you'll have lots of urea, but less water and salt compared to before when it goes in. Okay? So that is the whole process. I'm going to stop recording.